Now, he's doing his Euro tour. He's on his way to like many places around Europe. And we were discussing, and I thought, oh, that would be so nice if you were coming to the CRI. Brennan is at the Network Science Institute in Boston, which is in the physics department. And he's a fifth-year PhD student supervised by Alessandro Vespignani. He's actually a cognitive scientist originally, right? Perception, action, and now he's trying to understand how networks perceive and act, right? And part of the things that he's done at the Network Science Institute was also organizing collaborative methods development and collaborative, what we call collaborathon, around making network reconstruction algorithms and making a package to have methods available. And you're going to talk about all these things today. So we're very happy to have you here. And you have 40 minutes also.
Okay. Thanks, Mark. Also, thanks, everyone. The space is beautiful. Mark sent me a Twitter message like a year ago saying, Brennan, you have to come out to Paris. This place is way better than Nazi. Now, I couldn't think of many titles to what the talk's going to be about. I didn't want to name it like the rantings of a madman, but you'll notice that it'll hop around a lot. This is one version of the title. Another one is just that I like squirrels and foreheads and culture and science and networks. And I guess more generally, it's just about some of the stuff that I've been doing in my PhD. I have another year after this current one, but that year might take 10 years, so PhD forever. Like Mark said, I'm at the Network Science Institute in Boston. We're in that big tower right next to this big Florentine church. This is actually the Christian Science Church, and so fittingly, we call the tower the Network Science Church. And so, just a quick, I didn't know how much you knew about where Mark came from, but I just wanted to give a little bit of background. We have a bunch of network scientists who are faculty and then a bunch of affiliated faculty. They all have postdocs and there's independent researchers. And then I have 26 classmates. So we have a PhD program devoted to network science, which means that we don't have any skills that are core to the field, because I'm not sure there's any core network science skills. And so I see a lot of what motivates my work now is to try to figure out what is some core of network science, because I don't know, and I think it's a fun thing to think about. We make T-shirts a lot too. We try to
no advertisement. We said no advertisement.
Try to balance lots of disciplines. Also, a big distraction that I tend to do in my talks is I draw a lot, and so I'm just going to throw a bunch of art at you. Getting my PhD in network science, as Mark said, I got an undergraduate degree in cognitive science. My dissertation is about a teleology of networks, which essentially is just I overly anthropomorphize everything. So I think networks want things, and I'm trying to figure out what that is. I currently have a revise and resubmit from the Unicode Foundation for a network emoji to go on like all phones, hopefully. They didn't like the drawing, but they liked the rationale. And I did the drawing and Cynthia did the rationale. My favorite book's The Goldfinch, my favorite poems of those. This is my favorite GIF, and I'm going to use this a lot because it's actually quite indicative of my research style, which is just bouncing from topic to topic. These are 6 boxes. Some of the work that I've done this is all just preamble for what I'm actually going to talk about today too. In the past, I've done stuff on neuroscience and looking at the spread of the opioid epidemic in the United States. I have a colleague who does sex trafficking and labor trafficking research. Do stuff on optimal experimental design, so how to run maximally informative experiments. And then the things that I'm sort of most interested in is just abstract theory and philosophy in and of network science. So in particular, as it relates to causality in networks, but sort of more generally too. Recently, what's been getting me really excited is thinking about whether there is a theoretical framework to describe how networks merge. So in particular, in the context of eukaryogenesis, so maybe there were some early life forms that enveloped each other or in some way symbiotic. But what at the end of the day happened was that two networks that were once not the same organism might have become the same organism. And I don't think we have a good network theory of merger, so I would like to study that if anyone's interested in that. I went to a summer school this summer and met a lot of friends. One of them's a geomorphologist who can get all of the river data on Earth. And so we got all of the rivers and all of the river networks of Earth, and we're trying to look at basic properties of river networks. And then I've been getting more and more into protein networks lately. So this, some guiding questions about the talk, and then one day I'll actually start to talk about research. What is this?
Infinite sea of ideas.
Yeah, water, I would say. What is this? What is this? If I said it was a squirrel, I would have a reason for saying that, because this is just a chaotic mess of jumble. But the reason that I'm naming it that, the reason that I'm choosing to cast some representation of that very complicated set of colors, is that I want to tune your attention to something that's structurally going to persist in that mess. So eventually I can have this like scaffolding down of what is otherwise this really complex, dynamic, swirly, colorful thing to just get you a single thing that I can say, this is what's interesting about this system, and we're going to observe how it interacts with everything around it and how everything around it interacts with it. So that when you say this, you can say squirrel. So that, still vague. I'll go a little bit, teeny bit more specific. The basic premise is that we observe all sorts of complex processes around us, and I'm trying to look at the best way to represent those systems so that we can understand and intervene in them. Okay? So it's the 75th anniversary of this lovely monograph by Schrodinger. And in it, I think he gets at this quite nicely, which is this question about how the events in space and time, which take place within the spatial boundary of a living organism, how can those be accounted for by physics and chemistry? And if you take some liberties with the idea of a spatial boundary, so not necessarily like a cell in its milieu or us and our environment, but just some statistical boundary. So statistically, what is encapsulated by what you're calling the thing, so the squirrel, or whatever your representation is, and then everything that's not that. Still vague? So for today's talk, I'm just going to refer to those, I'm going to make a claim, I don't know if it's true, but let's just see where it goes, that a boundary between whatever you're talking about and whatever you're not talking about is necessary for any representation. And in the context of networks, what we often do in network science is we say, we're studying the thing, which is the network, but we don't have a good understanding of, or we don't maybe treat as heavily what's surrounding the network. So a lot of the stuff that I'm interested in focuses on looking at the sort of shadow world that's outside the network, that's maybe influencing the dynamics inside the network, which is possibly influencing the structure that we observe. Bouncing. I'm going to skip an example and talk about research. And then I might come back to the example. And I should also say that if at any point you want to ask questions, please feel free to. This was an example of how science progresses. I don't know how science progresses. Okay. So I'm going to do one more research-y motivated question. And then I'm going to talk about two main projects, the ones that were advertised on the email. And let's get into them. So the first one, does anybody know what this is? Square. It's a square. Does this give more context? Does anybody know what this is?
Yes, the Reddit, the map, like the war. Oh, beautiful.
Does anyone who's not marked
the Reddit
know what this
flag.
is?
As you will see.
Okay, so I'm using this as an example, but it's also a research project that some friends and I are working on. Yeah.
I always wanted to look at that.
Yeah.
Amazing.
Okay, so it's this square. If you imagine this square as a 1,000 by 1,000 pixel canvas. Currently, every pixel is white. And on Reddit.com, has anyone not heard of Reddit? Okay, it's the 5th biggest website in the world. Lots of traffic. Lots of people went to this page at this time, April 1st, 2017. So the rules are: this is an empty canvas. You may place a tile upon it, but you have to wait to place another. So I can change the color of any of the pixels, but I have to wait 5 minutes until I do another thing. Individually, you can create something. Together, you can create more. So what's going to happen?
Oh, it's going to look like cell automats, right? You're going to have like these patterns that are going to appear.
Yes. I really like.
If they didn't chat with each other, probably.
That's
Yeah,
right,
sure.
If they were independent.
Yeah.
They didn't chat with each other.
Yeah, I was in the independent.
Yeah. That's a social platform.
Okay.
I'm going to play out what happens. This is 72 hours, and I'm messing with the time a little bit, so it'll start slow, and then it'll pick up a lot, and then I'll replay it back. Deep breath. Okay. So, early on, I don't know if you can see this, a bunch of pixels are starting. So there's a scale at which, or there's a period of time where one person can meaningfully contribute to the overall canvas, let's say. But then, kind of quickly, you start to see crazy stuff happen, which is that collectives of people are saying, let's do something. Let's go to the bottom corner and make it all blue. Let's write like inappropriate words in green over there. Let's make maps and flags, and there's a German flag that's about to eat France. And this is all just individual people clicking and changing the color of a pixel in a million possible.
You know the $1 million page, right? From a few years back.
Yeah, it's more or less the same
a guy who I think for getting some money for his studies created a 1,000 per 1,000 web page, and basically you could pay $1 to get an advertisement on 1 pixel. And so the guy really quickly got his $1 million thing. You can check, it's a pretty ugly page because you have
and then if you zoom
commercials everywhere. Right?
So I'm going to play again real quick. The process that's happening to me is quite an interesting one. I think it's just universally quite interesting. But in particular, there's a notion that some structure, some boundary between the Mona Lisa and not the Mona Lisa emerges. It persists through time. There's literally someone like expending like 1,000th of a calorie to click their mouse somewhere in the world to make sure that this black void right here, when it starts to overtake, they don't want it to defeat the Mona Lisa, so they have to fight it off. So someone has to be like queued up, ready to go. So there's a structure that's actually that's needed to actually maintain that boundary between what is the Mona Lisa and what is not the Mona Lisa. It also seems like in like what you're saying about cellular automata, that there's just the sort of lowest common denominator of the cell is not the level of the like on-off or some gliders or something, but it's some cultural object. So like the smallest pixel then is a meme, maybe.
There is also a really interesting behavior that you see on the right side, where you have this field of green and white squares that is expanding, and you see that at some point you have noise that appear a lot on the picture, and that tends to then disappear as the figure enlarges, and then the noise reappears when you see that on the right.
Starting to make some grids.
Yeah, the grid, and so you will see that you have a lot of small pixels, noisy pixels that are popping in.
Because it's under attack, and then
exactly.
At a certain point, what the green grid.
So do you have a way to actually check the number of people that is participating on a specific part
but
of
they all
the
were on
picture?
forum
Or?
of Reddit. They were also on forum, no? You can.
I don't think you can trace who did what.
Mm-hmm.
You have the data? You have the data on who did what?
So if I were a more classical scientist, what I would say is, let's look at the mean pixel spot, here it is. But in a sense, it's clear that this isn't actually capturing what the fundamental process of this Reddit/place experiment is doing. And so as such, there's like a methodological interesting gap, which is like, how can you sort of automate the detection of interesting structure in this cultural object? And there's also a sociological thing, which is like some, this is like, so of course this happened. The Palestinian flag was being encroached on by the Israeli flag. And so people from the subreddit r/Palestine went to the r/Turkey subreddit and were like, can you help us fend off the encroaching flag? If not, can we come and like reposition our flag near you guys so we can have more like synchronies? So there's like a whole sociological side of it that's fascinating. There's a methodological side that I think is interesting too, because essentially this is fake data, but it would kind of look like this, which is just pixel ID on this side and then time on this side. And so you can say something like, maybe this chunk is Mona Lisa-esque, or this chunk is Rick from Rick and Morty. And so as like an algorithmic opportunity, it seems like a very fun one, because yeah, we kind of talked about it. But basically, data set. So if every pixel's color, every click of the canvas, every user who clicks it, the subreddits that user contributes to, and the comments and replies that that user is associated with. So just as a sort of primer to, I'm not going to talk about this anymore, but as a introduction to the things I really like to look at. Okay, so the main research that I've been doing over the last couple of years is not about Reddit, it's about networks, and it's about the emergence of sort of higher order informational structures in networks. And I'll get to unpack what that means, but essentially it's some buzzwords about it are that you might have heard of this phenomenon called causal emergence, which is when you can throw out some information and as a result you actually get a better, say, view of what can possibly cause what in this network. So we'll get into that. So the relevant paper that this is about is this one that my collaborator Eric Hoel and I put out this summer. And then we have a couple of applications and methodological additions to it. So what is this? It's a light bulb. The light bulb can be off. It can be on. If you have a light switch, then you have more states to the system. So the light switch and the light bulb can be off. The light switch and the light bulb can be on. Or you can have a bad electrician and maybe mix those two up. But the whole state space of this light bulb light switch system is these 4 states, and you can look at the transitions between states such that if I intervene in the system, I can make some sort of certain prediction about the state of another, or the transition of the other object, or just generally it's a system of 4 states. And I'm looking at how they transition from one to the other. And I'm looking at how to represent those transitions in an informative way. Informative being, I want bits of information. So if you think of, I tend to not like these types of examples of causal graphs because they're not the types of networks that I know and love, so I'm going to try to breeze through this. But essentially this is a copy gate, so if this is in state 0, this will copy it into, or no, if it's in state 0, 0, it will copy into state 0, 1, so that neighboring node will copy its neighboring node state. If this is 0 and this is 1, then swap. So if it's in this state of time t, it will be in that state of t plus 1. Another version of it is an AND gate. And so the only way that this can stay on as in 1 and 1, is if they're both already on. Otherwise, it's going to go to 0, 0, both off. So if you think of these 2 transition probability matrices in a sort of network scientific sense, you can just cross out transition probability and put adjacency. It's maybe a little bit crude to do that, but if this is suddenly our network that we're looking at, is this the best way to represent the causal structure of these two systems? And what the sort of goal of a lot of this work is, or not goal, but one of the outcomes of a lot of this work is that it may not be. So to kind of refresh this real quick, networks are often used to represent and model complex systems in this sense. So the squirrel is the whole dynamics of the swirly, colorful states, but it's not actually the squirrel, it's the model of it. And then the question that I'd like to ask is whether your representation of this system captures states or captures nodes that are necessary for maybe bringing about causes in other states. And the same is true with, does it capture connections that are sufficient? And these two words come up a lot, and I never knew what they meant, so I'm going to walk through them a little bit. So necessity, it's a past-present kind of thing. Yes?
The model that you were just showing before, does it work only with binary nodes or discrete nodes, or can you extend it to continuous?
Yes, it's that's a good question. I think it's possible, and I think actually people have reached out to try to work on it. I have no clue how to do it. But what I would do is just bin it in some way that discretized it. But it doesn't need to be binary.
Right.
And really, you can just give me any network, and I can just assume that this is sort of that a node is a state in a way, and that's comes with a lot of baggage, I think. But the process is a structural one, so all the things that I'm going to describe can be applied to just arbitrary networks. So necessity is a past to present type of interaction. So if a random walker on node B in the past is definitely going to transition to node A in the future, and B I can say is necessary for A, so that there's a necessary type of relationship. If C could also lead to A, B is no longer necessary, or maybe less necessary. If D can also lead to A, it's even less necessary. So if I'm at A right now, if I'm standing right here, there's a lot of possible ways that I could have come here, versus, which is a more uncertain past, versus a more certain past, which is, if I'm here, the only way I could have gotten here was the previous step. Sufficiency is a present to future type of relationship. So this is an example of A in the present being sufficient to cause B in the future. However, if A can also subsequently cause other things or bring about, or information can flow from A to C, then it's less sufficient for inducing B, and so on. And so you see these types of structures in networks all the time. So there's nodes with high in degree or high just degree in general, or varying amounts of degree. And I'm trying to basically just quantify what a given network has in terms of its certainty about future states and certainty about past states. And so there's a measure that will capture that, and I'm going to try to walk through the actual measure itself.